Welcome to AI Frontiers, where today we explore 17 groundbreaking computer vision research papers published on July 25, 2025. Picture this. While you were sleeping last night, researchers around the world were teaching machines to see hair as separate from faces, to understand the difference between spacecraft and stars, and to read graphical interfaces with unprecedented accuracy. Today's journey takes us beyond pixels into the sophisticated world of artificial visual intelligence, where machines are learning to truly see and understand our complex visual world. What awaits you in today's exploration is a comprehensive journey through visual intelligence breakthroughs that are reshaping how machines perceive and interact with the world. We'll discover how artificial systems are mastering compositional scene understanding, breaking down complex visual elements into manageable components. You'll explore revolutionary advances in three-dimensional reconstruction and avatar generation that bring digital humans to life with unprecedented realism. We'll examine efficiency innovations that make sophisticated AI vision accessible across diverse deployment scenarios, from powerful data centers to mobile devices. Our investigation covers specialized applications spanning medical imaging analysis to space exploration challenges, and will uncover the future research directions that promise to transform computer vision even further. Computer vision represents the ambitious goal of teaching machines to see and understand visual information the way humans do naturally. This field transforms raw pixel data into meaningful understanding, powering everything from the face recognition that unlocks your smartphone to the sophisticated perception systems guiding autonomous vehicles through city streets. The challenge lies in bridging what researchers call the semantic gap, the vast difference between numerical pixel values and the rich, contextual understanding that humans effortlessly extract from visual scenes. The field has undergone dramatic transformation over the past decade, evolving from traditional handcrafted feature extraction methods to deep learning approaches that automatically discover relevant visual patterns. Today's systems must process the millions of images and intros generated globally every minute, requiring increasingly sophisticated algorithms to handle variations in lighting, perspective, occlusion, and countless other factors that make real-world vision incredibly complex. The first major theme emerging from these 17 papers centers on a revolution in three-dimensional scene understanding, marking a fundamental shift from traditional two-dimensional image analysis to comprehensive spatial reasoning. Neuro-radiance fields have emerged as a powerful technique for enabling photorealistic three-dimensional reconstruction from limited input data. Kim and colleagues introduced the HairCUP research, which tackles the sophisticated challenge of creating three-dimensional head avatars with explicit hair compositionality, addressing the fundamental problem of disentangling facial and hair commissures in three-dimensional space. Gaussian splatting techniques are accelerating real-time three-dimensional scene generation, offering dramatic improvements in training and inference speed, while maintaining visual quality. Researchers are also tackling the unique challenges of spacecraft modeling, where traditional assumptions about lighting and background simply don't apply in the vacuum of space. This theme represents a movement beyond flat image analysis toward machines that can reason about depth, spatial relationships, and three-dimensional structure with human-like sophistication. The second dominant theme involves the integration of multimodal learning, specifically bridging vision and language understanding in unprecedented ways. This reflects the growing recognition that true artificial intelligence requires the ability to understand and reason across multiple types of sensory information simultaneously. Vision language models are now processing visual and textual information together, enabling systems that can look at images and describe them in natural language, answer complex questions about visual content, and even generate similar images based on textual descriptions. The circuit probe research introduces systematic methods for understanding how large vision language models process spatio-temporal visual semantics, revealing fascinating insights about how these models internally represent and manipulate visual concepts in conjunction with linguistic understanding. This breakthrough represents a fundamental advance in creating AI systems that can engage with visual information in more human-like ways, breaking down the traditional barriers between different types of sensory information processing and enabling more sophisticated multimodal reasoning capabilities. The third and fourth themes focus on efficiency, optimization, and specialized domain applications, addressing the practical challenges of deploying sophisticated AI in real-world scenarios. Zhu and colleagues introduced the EA-ViT framework, which demonstrates how a single training process can efficiently generate multiple model variants optimized for different computational constraints, from powerful cloud servers to resource-limited mobile devices. This approach represents a paradigm shift from training separate models for different deployment scenarios toward more flexible adaptive systems. Specialized applications showcase how general computer vision techniques are being adapted for unique domain requirements. Medical imaging advances in chest X-ray classification demonstrate sophisticated approaches to handling class imbalance in clinical findings, while robot soccer applications show how even seemingly simple tasks like line detection can benefit from domain-specific optimization. These themes highlight the critical balance between computational resources and performance requirements, making sophisticated AI vision accessible across diverse deployment scenarios and specialized use cases. Several revolutionary findings emerge from this rich collection of research that have the potential to significantly impact the entire computer vision field. The first major breakthrough demonstrates that compositional modeling approaches, which explicitly separate different visual components like hair and facial features, dramatically improve three-dimensional avatar generation quality and controllability. This finding suggests that many computer vision tasks could benefit from hierarchical approaches that model the modular nature of visual scenes. The second significant discovery reveals that visual grounding accuracy serves as the primary determinant of overall success in GUI automation scenarios, challenging common assumptions that sophisticated reasoning capabilities matter most. The third breakthrough shows that a single training process can generate multiple efficient model variants, achieving up to an order of magnitude reduction in training costs, while maintaining competitive performance. Additionally, self-supervised visual representations are becoming increasingly universal, with DINO-based approaches showing success across multiple applications. Finally, specialized evaluation frameworks are revealing hidden limitations in current models, emphasizing the need for more comprehensive assessment methodologies that consider multiple dimensions beyond simple accuracy metrics. The methodological innovations driving these advances showcase several approaches that represent the current state-of-the-art in computer vision research. Radiance fields and Gaussian splatting have revolutionized three-dimensional scene reconstruction by learning continuous functions that map spatial coordinates to visual properties, enabling photorealistic image generation from arbitrary viewpoints. Self-supervised learning has become dominant through teacher-student knowledge distillation frameworks, where teacher networks provide supervision without requiring manually annotated data, enabling training on vast amounts of unlabeled visual information. Vision transformers have brought attention-based mechanisms from natural language processing to visual understanding, treating images as sequences of patches and applying self-attention to capture long-range dependencies in visual data. Diffusion models have emerged as powerful alternatives to generative adversarial networks, offering improved training stability for high-quality image generation by learning to reverse gradual noising processes. Elastic architectures represent a new paradigm that can dynamically adapt to different computational constraints, providing flexibility in deployment while maintaining performance quality across diverse scenarios. The HairCUP research by Kim and colleagues represents a seminal contribution to controllable three-dimensional head avatar generation with explicit hair compositionality. This work addresses a fundamental limitation in existing avatar generation methods that treat hair and facial features as inseparable components, leading to entangled representations where modifying hair affects facial features and vice versa. The research's innovative methodology involves creating a synthetic hairless data generation pipeline using sophisticated diffusion model in painting techniques, allowing them to train separate encoders for facial and hair components while maintaining their spatial relationships. The technical innovation extends to the latent space design, where separate latent codes control facial and hair feature independently, enabling unprecedented control over avatar appearance. Users can modify hairstyles, colors, and textures without affecting underlying facial characteristics, and the approach enables mixing and matching hairstyles across different individuals. The experimental results demonstrate substantial improvements in both visual quality and controllability compared to existing methods, with implications extending beyond entertainment to virtual try-on systems, personalized avatars for virtual meetings, and forensic reconstruction applications. The MMBench-GUI research by Wang and colleagues provides comprehensive evaluation of multimodal large language models on graphical user interface, understanding tasks, addressing a critical gap in understanding how well current AI systems can interact with graphical interfaces. This capability is becoming increasingly important as we move toward more autonomous AI agents that need to navigate complex digital environments. The research methodology involves creating a comprehensive benchmark that evaluates models across multiple dimensions of GUI understanding, including visual grounding, spatial reasoning, and tasks completion efficiency across diverse interface types, from mobile applications to desktop software. The key finding that visual grounding accuracy serves as the primary determinant of overall task success challenges prevailing assumptions about AI agent capabilities, revealing that even state-of-the-art models struggle with accurate visual localization in GUI contexts. The introduction of the efficiency quality area metric provides a more nuanced view of agent performance by considering both tasks completion success and execution efficiency, revealing that many current models suffer from substantial inefficiencies with excessive redundant steps. This work provides a template for evaluating AI agent in other complex multi-step reasoning scenarios. The EA-ViT framework by Zhu and colleagues addresses the critical challenge of efficiently adapting vision transformers for different deployment scenarios, recognizing that the same model architecture may need to operate under very different resource constraints. The research methodology introduces an elastic architecture approach that can generate multiple model variants from a single training process, dramatically reducing overall training costs while providing deployment flexibility. Rather than training separate models for different resource constraints, the EA-ViT framework learns a supernet containing multiple subnetworks with different computational complexities. The technical innovation lies in adaptive depth and worth scaling mechanisms that allow dynamic capacity adjustment based on available computational resources, including sophisticated parameter sharing techniques across different model variants, while maintaining performance quality. The training process involves progressive shrinking strategies that gradually reduce model capacity while preserving learned representations. Experimental results demonstrate remarkable efficiency gains, achieving up to an order of magnitude reduction in training costs compared to training multiple separate models, while maintaining competitive performance across different model sizes, with significant implications for practical deployment scenarios. Looking toward the future, several significant challenges and opportunities emerge from this research that will shape the trajectory of computer vision development. The first major challenge involves scaling these sophisticated approaches to even larger models and more complex scenarios, while maintaining computational efficiency and performance quality. As vision transformers grow in size and capability, developing more sophisticated compression and adaptation techniques becomes increasingly critical. The second challenge relates to improving robustness and reliability across different domains and conditions, as real-world deployment often reveals brittleness when systems face distribution shifts, adversarial inputs, or unexpected scenarios that weren't present in training data. The third challenge involves bridging gaps between different modalities to create truly unified understanding systems that can seamlessly integrate visual, auditory, textual, and other sensory information through more sophisticated fusion mechanisms and training paradigms. The fourth challenge centers on democratizing access to advanced computer vision capabilities, making state-of-the-art models accessible to broader ranges of users and applications through continued focus on efficiency, ease of use, and automated optimization techniques. Transparency in our content creation process is essential for maintaining trust and accuracy in research communication. The content you're hearing today has been synthesized using advanced GPT and CLAUDE-SONNET-4-20250514 language models, which processed and analyzed the original research papers to create coherent, accessible explanations of complex technical concepts. Text-to-speech synthesis is powered by Deepgram technology, converting our written analysis into the natural-sounding narration you're experiencing. Image generation and visual enhancements are created through Google's artificial intelligence systems, providing visual aids that complement the technical discussions. Throughout this process, human expert review has been conducted to ensure accuracy, coherence, and faithful representation of the original research findings. While we strive for complete accuracy in our synthesis and presentation, we acknowledge the potential for oversights or misinterpretations in complex technical material, and we provide complete references to original sources so listeners can verify and explore the research independently. Join the growing AI Frontiers community by subscribing to our YouTube channel, where we provide daily breakdowns of cutting-edge research across computer vision, natural language processing, robotics, and emerging artificial intelligence fields. Our mission is to stay ahead of the latest breakthroughs and make sophisticated research accessible to developers, researchers, and technology enthusiasts worldwide. By subscribing, you'll get notified immediately when new research synthesis videos are published, ensuring you never miss important developments that could impact your work or interests. Join thousands of others who are exploring the future of artificial intelligence through our comprehensive analysis and expert commentary. Be part of the community that's actively shaping AI's future by staying informed about the latest discoveries and participating in discussions about their implications. Your subscription helps us continue bringing you high-quality analysis of the research that's defining tomorrow's technology landscape. AI Frontiers serves as your gateway to tomorrow's technology today, providing daily synthesis of cutting-edge artificial intelligence research papers with expert analysis that makes complex research accessible to everyone. We cover the full spectrum of AI advancement, from computer vision breakthroughs like those we explored today, to natural language processing innovations, robotics developments, and emerging fields that are reshaping our technological landscape. Our mission focuses on building bridges between academic research and practical applications, helping you understand not just what's being discovered, but how these discoveries might impact real-world applications and future developments. Subscribe now to ensure you never miss a breakthrough discovery that could influence your field or spark new ideas for your own projects. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses ropreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprintserver.org.